Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into one of Earth's most mysteriously peaceful chapters, the boring billion. That vast stretch of geological time when our planet seemed to pause and breathe. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The quiet eon begins around 1.8 billion years ago, when Earth settles into what scientists call the most stable period in its entire history. For 1,000 million years longer than complex life has existed, longer than continents have held their current shapes, the planet enters a state of chemical and biological equilibrium so profound that geologists struggle to find dramatic events to mark the passing time. The Great Oxygenation Event has ended, leaving oxygen levels hovering at perhaps 10% of today's atmosphere, and there they remain, barely fluctuating, as if the planet has found its perfect breath and decided to hold it. This is the Mesoproterozoic era, though few people learn its name. It spans from 1.6 to 1.0 billion years ago, nestled within the longer Proterozoic eon like a quiet room in a vast, ancient house. The very rocks from this time period speak of stillness, endless layers of sediment deposited year by year in shallow seas, each thin band a season's worth of patient accumulation. Geologists call these formations monotonous in their technical papers, and they mean it as a compliment of sorts. Only a planet at profound peace with itself can lay down such regular, undisturbed records. The word boring itself carries a peculiar weight when applied to a billion years. Modern humans struggle to comprehend even a single million years, yet here lies a stretch of time 1,000 times longer, marked by what appears to be cosmic patience rather than cosmic drama. If Earth's entire history were compressed into a single day, the boring billion would occupy nearly 3 hours. 3 hours of what seems like geological meditation, of chemical systems finding their rhythm and holding it with the persistence of breathing. Yet, beneath this apparent tedium, something almost paradoxical unfolds. The very stability that makes this eon seem boring creates the perfect conditions for life's next great evolutionary leaps. Like a long, slow inhale before transformation, Earth gathers its chemical and biological resources, allowing innovations to emerge in the ocean's quiet depths that will later reshape every living thing. The planet takes its time, as if it has learned that the most profound changes require the deepest stillness to take root. During these billion years, the sun burns steadily brighter, increasing its luminosity by nearly 10%. This gradual warming should have triggered dramatic climate changes, yet Earth's surface temperature remains remarkably stable. The planet's carbon cycle adjusts with exquisite precision, weathering rocks faster as temperatures rise, pulling carbon dioxide from the atmosphere at exactly the rate needed to maintain equilibrium. It is as if Earth develops a thermostat during this time, learning to regulate its own temperature with the skill of a master craftsman. The oceans themselves hold secrets that will not be fully understood for centuries to come. Their depths remain largely free of oxygen, creating vast zones where ancient chemistry continues to unfold. Iron dissolves into the water column and settles out again in regular patterns, painting the seafloor in bands of red and black that will puzzle future geologists. These banded iron formations disappear from the rock record during the boring billion, not because iron stopped cycling, but because the process becomes so steady, so reliable, that it leaves less dramatic traces. Volcanic activity, too, finds a quieter rhythm. The massive flood basalts that marked earlier eons fade into memory, replaced by more modest eruptions that build islands and reshape coastline, grain by grain rather than continent by continent. Even the planet's magnetic field settles into longer periods between reversals, as if Earth's molten iron core has learned the value of consistency. The first hint that this stability might be deceptive comes from studying the planet's rotation. During the boring billion, Earth spins faster than it does today. A day lasts perhaps 18 hours rather than 24. The moon hangs closer in the sky, its gravitational pull stronger, creating tides that surge higher up ancient beaches. These tides stir the shallow seas where much of life makes its home, preventing stagnation even as larger systems find their equilibrium. Continental drift continues its patient work, though at rates so slow that entire mountain ranges rise and erode away without leaving clear traces in the geological record. Supercontinents assemble and fragment like slow-motion kaleidoscopes, their movements governed by forces deep within Earth's mantle that operate on timescales measured in hundreds of millions of years. The continents themselves grow larger during this time, as volcanic island arcs collide and merge with their edges. But even this growth happens with geological discretion. Perhaps most mysteriously, life itself seems to pause during these billion years, as if evolution takes a sabbatical. The fossil record becomes sparse, dominated by simple microbial communities that build layered structures called stromatolites in shallow seas. These bacterial mats represent some of the most successful organisms in Earth's history, thriving in the same basic form for billions of years, yet their very persistence suggests a world where evolutionary pressure remains low, where innovation moves at the speed of stone. The irony settles over deep time like sediment in still water. This supposedly boring billion years may have been the most important 1,000 million in Earth's history, precisely because nothing dramatic seemed to happen. During this vast quiet, life experiments with cellular complexity in ways that will make possible every plant, animal, and fungus that will ever exist. The planet's chemical systems find rhythms so stable they will support an explosion of biological diversity unlike anything seen before or since. Scientists studying this period face their own quiet mystery: how to read the story written in rocks that seem to have little story to tell. The very abundance of ordinary sedimentary layers becomes its own form of evidence. Testimony to a planet so stable that the most dramatic event in any given million years might be a slight shift in sea level or a volcanic eruption on a distant continent. It is geology's equivalent of a long, peaceful sleep, restful, necessary, and pregnant with dreams of transformation to come. The planet's breathing finds its rhythm as oxygen levels hover in that strange middle ground between too little and too much. At 10% of modern concentrations, Earth's atmosphere holds just enough of this reactive gas to rust iron and support complex chemistry, but not enough to fuel the combustion that will later power multicellular life's great expansion. The air itself becomes a study in chemical patience, maintaining this delicate balance for hundreds of millions of years while volcanic outgassing and bacterial photosynthesis dance their slow waltz of production and consumption. This atmospheric equilibrium represents one of the most remarkable regulatory feats in planetary history, though it unfolds so gradually that no observer could witness its precision. Cyanobacteria continue their ancient work of splitting water molecules and releasing oxygen, just as they have for hundreds of millions of years. But now, their output matches almost exactly the planet's capacity to absorb this corrosive gas through rock weathering and organic burial. The result is a kind of atmospheric meditation, where oxygen levels rise and fall within narrow bounds like the breath of a sleeping world. Scientists puzzle over what they call the oxygen gap, the mysterious mechanism that prevents atmospheric oxygen from climbing toward modern levels during these billion years. Some propose that sulfur bacteria in the ocean depths consume organic matter so efficiently that little carbon gets buried, keeping oxygen production in check. Others suggest that volcanic activity, though quieter than in earlier eons, still releases just enough reducing gases to balance the atmosphere's oxidizing power. The truth likely involves a symphony of feedback loops, each one tuned with exquisite sensitivity to maintain the planet's chemical composure. The oceans themselves become vast laboratories of atmospheric regulation. Their surface waters hold dissolved oxygen from contact with the air above, creating thin zones where oxygen-breathing organisms can experiment with new forms of metabolism. But below these oxygenated layers, ancient chemistry persists in waters that have remained unchanged since the Archean eon. Here, in depths measured in hundreds of meters, bacteria continue to breathe sulfur and iron just as their ancestors did billions of years earlier, creating a layered world where past and future coexist in the same water column. This stratified ocean structure proves remarkably stable, maintained by the gentle circulation patterns that developed during the boring billion. Without the dramatic temperature gradients that drive vigorous mixing in later eons, the seas settle into lazy patterns of flow that allow chemical boundaries to persist for millions of years at a time. Oxygen-rich surface waters spread across the continental shelves like a thin blanket, while the deep ocean maintains its ancient reducing chemistry, turning slowly in currents so gentle they barely disturb the sediment on the seafloor. The chemistry of these deep waters creates one of the period's most beautiful mysteries. Dissolved iron gives the abyssal depths a slight greenish tint, while hydrogen sulfide lends them the faint scent of eggs gone bad, though of course, no nose exists yet to detect such subtleties. These chemical signatures will disappear from the ocean's depths during later eons, making the boring billion perhaps the last time Earth's seas carry the full aromatic complexity of their primordial chemistry. Phosphorus, that essential element for all life, cycles through this stratified ocean system with clockwork regularity. In the oxygenated surface waters, it gets bound up in iron minerals and settles toward the depths. But in the oxygen-free depths, it dissolves back into solution, creating upwelling currents rich in this vital nutrient that feeds the photosynthetic communities at the surface. This phosphorus pump operates for hundreds of millions of years without significant change, supporting steady populations of marine microbes while preventing the explosive blooms that might destabilize the system. The planet's carbon cycle, too, finds its own meditative rhythm during these billion years. Atmospheric carbon dioxide levels remain low enough to prevent runaway greenhouse warming, but high enough to support robust photosynthesis in the shallow seas. The steady weathering of continental rocks consumes carbon dioxide at predictable rates, while volcanic outgassing replenishes it with equally reliable persistence. It is as if Earth develops a carbon thermostat during this time, automatically adjusting its atmospheric composition to maintain surface temperatures within narrow bounds. Perhaps most remarkably, this atmospheric stability persists even as the sun grows steadily brighter throughout the boring billion. Solar luminosity increases by nearly 10%. During this time, a change that should drive significant climate warming. Yet, geological evidence suggests that global temperatures remain remarkably constant, varying by only a few degrees across hundreds of millions of years. The planet's regulatory systems compensate for increased solar heating with the precision of a master engineer, though the mechanisms involved remain partly mysterious even to modern science. The very air above the continents carries hints of this chemical stability, Dust particles blown from the gradually weathering rocks maintain consistent mineral compositions for millions of years at a time, as if the planet's surface chemistry has found its perfect expression and sees no need to change. Even the composition of rainwater remains remarkably constant, delivering the same balanced mixture of nutrients to terrestrial environments across vast spans of time. This atmospheric equilibrium creates conditions unlike any that will exist again in Earth's history. The air is thin enough that ultraviolet radiation penetrates to the surface more easily than in later eons, yet thick enough to maintain a stable greenhouse effect. It is rich enough in carbon dioxide to support photosynthesis, yet poor enough to avoid the climate instability that higher concentrations might bring. Like a perfect tuning fork, Earth's atmosphere finds its resonant frequency and maintains it with the persistence of physics itself. The irony of this chemical stability is that it makes possible the very changes that will eventually end it. The steady, predictable flow of nutrients through ocean and atmosphere creates ideal conditions for life to experiment with new forms of complexity, laying the groundwork for evolutionary innovations that will later transform the entire planetary system. Only during such a long period of chemical peace can life develop the sophisticated cellular machinery that will make possible the oxygen-rich atmosphere of later eons. Scientists studying atmospheric samples trapped in ancient rocks find themselves reading the chemical diary of a planet at rest, each measurement revealing the remarkable precision with which Earth maintained its atmospheric balance during these billion quiet years. Across the shallow seas of this quiet world, bacterial communities spread their patient architecture like living carpets woven from time itself. These microbial mats, composed primarily of cyanobacteria and their companion organisms, build structures called stromatolites, layered domes and columns of limestone that rise from the seafloor grain by microscopic grain. Season by season, century by century, each thin layer represents a community's daily work of photosynthesis and mineral precipitation, creating geological monuments to the persistence of simple life. The stromatolites of the boring billion grow with a regularity that borders on the meditative. During daylight hours, cyanobacteria migrate upward through the mat, following the sun's rays and leaving behind a film of sticky mucus that traps sediment particles. At night, they retreat slightly deeper, allowing the trapped material to settle and harden into a new layer of rock. This daily rhythm, repeated millions of times, builds structures that can reach several meters in height bacterial cities constructed at the pace of stone formation, where the only residents are microbes and the only architecture is chemistry. These microbial metropolises represent some of the most successful ecosystems in Earth's history, thriving virtually unchanged for billions of years across the planet's shallow marine environments. Unlike the dramatic evolutionary experiments that will characterize later eons, stromatolite communities perfect the art of stability, finding ecological strategies so robust they require no modification across hundreds of millions of years. It is life's equivalent of discovering the perfect note and holding it across geological time. The bacterial mats themselves harbor a complexity that belies their simple appearance. Within each layer, different species of microbes occupy distinct chemical niches, creating vertical ecosystems only millimeters thick but rich in metabolic diversity. Near the surface, cyanobacteria harvest sunlight and split water molecules, releasing oxygen into the surrounding water. Just below them, purple and green sulfur bacteria capture different wavelengths of light, using hydrogen sulfide instead of water for their photosynthesis. Deeper still, anaerobic bacteria break down organic compounds in the absence of oxygen, completing nutrient cycles that will sustain these communities for millions of years. This layered organization creates what scientists call a microbial mat ecosystem, a self-contained world where every waste product of one organism becomes food for another. The oxygen produced by surface cyanobacteria gets consumed by aerobic bacteria just beneath them, preventing it from penetrating deeper into the mat, where it might disrupt the ancient chemistry that still thrives in oxygen-free environments. It is a biological stratification as precise as the ocean's chemical layers, maintained by organisms that have learned to share space across microscopic distances. The daily migration of cyanobacteria through these mats creates some of the most beautiful patterns preserved in ancient rocks. As the bacteria move upward toward the light each morning, they leave behind trails in the sediment that form delicate laminations visible to modern geologists examining stromatolites under microscopes. These bacterial highways, preserved in stone for billions of years, record the daily routines of organisms whose descendants still follow similar patterns in modern microbial mats. During the boring billion, stromatolite reefs spread across vast areas of the continental shelves, creating underwater landscapes unlike anything that exists today. These bacterial cities rise from the seafloor in domes and towers, their surfaces rippling gently in the tidal currents, their communities pulsing with the rhythms of photosynthesis and respiration. Between the stromatolites, sandy channels wind like bacterial boulevards, carrying nutrients and waste products in slow circulation patterns that serve these ancient ecosystems with the reliability of metabolic bloodstreams. The very success of these microbial communities during the boring billion points to one of the period's central mysteries. Why does evolution seem to slow to a crawl during these billion years? The stromatolite record shows little change in community structure or bacterial diversity across vast spans of time, as if life has discovered optimal solutions and sees no need for innovation. Some scientists suggest that the stable chemical conditions create environments so predictable that evolutionary pressure remains low, allowing successful strategies to persist without modification for hundreds of millions of years. Yet, within this apparent evolutionary stasis, subtle changes unfold that will prove crucial for life's future development. The steady oxygen production by stromatolite communities gradually increases the availability of this reactive gas in shallow marine environments, creating new ecological niches for organisms that can tolerate or even require oxygen for their metabolism. These oxygenated zones around stromatolite reefs become testing grounds for biochemical innovations that will later reshape the entire biosphere. The bacterial mats also serve as natural laboratories for symbiosis, the close association of different species that will become one of evolution's most powerful tools. Within the layered communities of stromatolites, bacteria that produce oxygen live in intimate contact with bacteria that consume it. Bacteria that fix nitrogen share space with bacteria that require it, and bacteria that produce organic compounds coexist with bacteria that decompose them. These symbiotic relationships, refined over hundreds of millions of years in the stable environment of boring billion stromatolites, provide the foundation for the complex cellular partnerships that will later make possible all multicellular life. The patience of these bacterial builders becomes almost incomprehensible when measured against human timescales. A single stromatolite dome that rises 3 meters from the seafloor represents perhaps 50 million years of daily microbial labor, longer than the entire evolutionary history of primates, achieved through the accumulated work of organisms too small to see without magnification. Each morning's upward migration, each night's settlement, each season's growth adds another microscopic layer to structures that will outlast continents. Modern scientists studying ancient stromatolites find themselves examining the fossilized remains of communities that knew only the present moment, yet whose collective work shaped the future of the entire planet. In the layered limestone of these bacterial monuments lies evidence of life's first great lesson in patience, that the most profound transformations arise not from dramatic changes, but from simple processes repeated with the persistence of stone formation itself. The irony embedded in these ancient reefs whispers across deep-time organisms that never evolved, never changed, never adapted to new conditions. Nevertheless, created the environmental conditions that would make possible evolution's greatest innovations. The continents themselves begin their slow dance of assembly and separation during these billion quiet years, moving across Earth's surface at rates measured in centimeters per century speeds, so gradual that entire mountain ranges can rise and erode away between the collision and separation of land masses. The supercontinent Columbia, assembled during the earlier Paleo-Proterozoic era, begins its patient fragmentation around 1.5 billion years ago, its pieces drifting apart like puzzle fragments floating on the planet's molten mantle. This continental drift operates according to forces generated deep within Earth's interior, where radioactive decay heats rock until it flows like thick honey, carrying the lighter continental masses along in currents so slow they make geological time itself seem hurried. The breakup of Columbia unfolds across hundreds of millions of years, each stage marked by the opening of new ocean basins and the gradual separation of land masses that will not meet again for another billion years. As the continental fragments drift apart, new oceanic crust forms in the widening gaps, adding to the planet's surface area grain by grain through volcanic processes that operate with the patience of planetary breathing. Mid-ocean ridges spread at rates of a few centimeters per year, extruding fresh basalt that cools and solidifies into new sea floor, pushing the continents farther apart in a process so gradual that it becomes almost meditative in its persistence. This continental dispersal creates new patterns of ocean circulation that will influence global climate for hundreds of millions of years. As the fragments of Columbia drift into different latitudes, they alter the flow of surface currents and deep water circulation, establishing climate patterns that favor the continued stability of the boring billion. Isolated continental masses develop their own weathering patterns, each one contributing to the global carbon cycle in slightly different ways, yet all of them maintaining the overall chemical equilibrium that characterizes this quiet eon. The geology of these drifting continents tells stories of gradual transformation written in rocks that accumulate layer by patient layer. Sedimentary basins form in the spaces between separating land masses, filling with the eroded remains of ancient mountains, transported grain by rivers that flow for millions of years without changing their basic courses. These sedimentary sequences, some reaching thousands of meters in thickness, represent the patient work of weathering and erosion operating at rates so slow that they make human history seem instantaneous by comparison. Mountain building during the boring billion follows similarly gradual patterns, as continental fragments occasionally collide at convergent margins to create new ranges through processes that unfold over tens of millions of years. These orogenic events operate without the dramatic intensity that characterizes mountain building in later eons, producing ranges that rise and erode with equal patience, their peaks wearing down almost as quickly as they form. The very rocks within these ancient mountains show evidence of slow deformation, folding and faulting at rates that allow minerals to recrystallize and reorganize their internal structures without the brittle fracturing that marks more rapid tectonic processes. Volcanic activity associated with this continental drift maintains the subdued character that marks all geological processes during the boring billion. Rather than the massive flood basalts that punctuate earlier and later eons, volcanic eruptions during this time tend towards smaller, more regular events that add to the continental margins incrementally rather than catastrophically. Island arcs form in the ocean basins between the drifting continental fragments, building volcanic chains that will eventually collide with continental margins to add new territory to the growing land masses. But even these processes unfold with geological discretion. The very composition of the continental crust begins to change during these billion years, as the gradual processes of weathering, erosion, and redeposition sort and concentrate different mineral components. Granitic rocks, rich in silica and aluminum, become more common as the lighter components of the crust get recycled through multiple episodes of erosion and sedimentation. This chemical evolution of the continents creates land masses that are more buoyant and stable than their Archean predecessors, contributing to the overall geological tranquility that characterizes the period. Perhaps most remarkably, the continental drift of the boring billion operates without triggering the massive climate changes that similar processes cause during other eons. The gradual nature of the breakup, combined with the stable atmospheric composition of the period, allows global climate to adjust smoothly to new continental configurations. Ocean currents shift gradually as new passages open between land masses, but these changes unfold slowly enough that biological communities can adapt without mass extinctions or ecological disruptions. The breakup of Columbia also influences the planet's magnetic field in subtle ways, as the changing distribution of continental masses alters the flow patterns in Earth's molten iron core. The magnetic field itself remains more stable during the boring billion than during most other periods, with fewer reversals and longer periods of consistent polarity. This magnetic stability may contribute to the overall tranquility of the period, protecting the planet's surface from some of the cosmic radiation that might otherwise drive more rapid evolutionary change. Between the separating continental fragments, new ocean basins mature slowly from narrow rifts into broad seas. The Red Sea of today provides a modern analogy for these ancient processes, though the rifting of the boring billion unfolds over timescales an order of magnitude longer. These growing ocean basins develop their own circulation patterns and chemical characteristics, creating new marine environments that will host their own communities of stromatolite-building bacteria and other simple organisms. The sedimentary records preserved in these ancient continental margins reveal the remarkable regularity of geological processes during the boring billion. Layer after layer of marine sediments accumulates in predictable patterns, with few of the dramatic unconformities or volcanic interruptions that characterize rocks from more active periods. It is as if the planet learns during these billion years to change its surface configuration gradually, avoiding the sudden movements that might disrupt the chemical and biological equilibria that define the period. Scientists studying the continental drift of the boring billion find themselves reading geological stories written in a language of gradual change, where the most dramatic events unfold over time scales longer than entire evolutionary lineages persist in later eons. The very rocks seem to embody the patience that characterizes this quiet chapter of Earth's history. Their mineral grains aligned and recrystallized through slow deformation that allows stone itself to flow like viscous fluid over geological time. Beneath the waves, in the deep ocean's perpetual darkness, chemical reactions unfold with the patience of planetary breathing, creating a hidden world of molecular transformations that will remain invisible to any observer for billions of years. The deep waters of the boring billion carry dissolved iron in concentrations that would turn the seas rust red if oxygen ever penetrated to these depths. But the oxygen never arrives. Instead, ancient chemistry persists in the abyss, where iron and sulfur compounds dance their slow molecular ballet, in waters that have remained chemically unchanged since the Archean eon. This deep ocean chemistry creates one of the most remarkable features of the boring billion, a vast reservoir of chemical potential energy stored in the dissolved metals and gases that accumulate in the oxygen-free depths. Iron exists in its reduced form, dissolved as invisible ions that give the deep waters a faint greenish tint, detectable only in the thickest columns of liquid. Manganese, too, remains dissolved in concentrations that would be impossible in an oxygenated ocean, creating a chemical soup rich in the metals that will later become essential components of complex biological molecules. The boundary between the oxygenated surface waters and the anoxic depths creates one of the most chemically active zones in the ancient ocean, though this activity unfolds at rates measured in geological time rather than biological time. Here, where oxidized and reduced chemical species meet. Precipitation reactions create thin layers of metal-rich sediments that settle toward the seafloor like molecular snow. These chemical boundaries shift up and down in the water column with changes in ocean circulation and atmospheric composition, but they remain remarkably stable throughout the boring billion, creating persistent chemical gradients that will influence marine ecosystems for hundreds of millions of years. Hydrogen sulfide bubbles up from the deep ocean's chemical reactions, creating concentrations that would be toxic to most modern marine life. Yet this gas represents the primary energy source for vast communities of bacteria that thrive in the oxygen-free depths. These sulfur-breathing organisms, descendants of Earth's earliest life forms, continue their ancient metabolisms in the deep waters, processing the chemical byproducts of rock weathering and organic decay with the same biochemical pathways their ancestors used billions of years earlier. Their metabolism produces organic compounds that drift upward through the water column, feeding other communities and creating chemical cycles that span the entire ocean depth. The deep waters also serve as a vast reservoir for phosphorus, that essential element that limits biological productivity in many marine environments. In the absence of oxygen, phosphorus remains dissolved in the deep ocean rather than getting bound up in iron minerals as it does in oxygenated waters. This dissolved phosphorus gets carried to the surface by the slow, upwelling currents that characterize boring billion oceanography, creating a steady supply of this crucial nutrient that supports the stromatolite communities and other simple organisms living in the shallow seas. The phosphorus cycle operates like a vast biological pump, moving nutrients from the depths to the surface with the reliability of a planetary circulatory system, perhaps most mysteriously. The deep ocean chemistry of the boring billion creates conditions that may actually inhibit evolutionary innovation. The stable chemical environment provides few selective pressures that might drive organisms toward greater complexity, while the abundance of dissolved nutrients ensures that even simple metabolisms can support thriving populations. It is as if the ocean's chemistry creates a biological comfort zone so complete that life sees no need to experiment with new forms or functions. Carbon cycling in these deep waters follows patterns that will not be seen again once oxygen penetrates to the ocean floor. Organic matter that sinks from the surface waters gets decomposed by anaerobic bacteria using sulfur and iron compounds instead of oxygen, creating different end products than modern decomposition processes. This anaerobic decomposition is less efficient than aerobic decay, meaning that more organic carbon gets buried in the sediments, helping to maintain the atmosphere's low oxygen levels by preventing the release of gases that would react with atmospheric oxygen. The chemistry of these deep waters also preserves a remarkable record of the planet's early atmospheric composition. Gases dissolved in the ocean depths reflect the composition of the atmosphere at the time they last contacted the surface, and the slow circulation patterns of the boring billion mean that some deep waters carry chemical signatures that are hundreds of years old. These ancient chemical fingerprints, preserved in the molecular composition of seawater, provide scientists with indirect measurements of atmospheric chemistry from periods when direct atmospheric samples are impossible to obtain. Rare earth elements accumulate in the deep waters through the gradual weathering of continental rocks, creating concentrations of these exotic metals that far exceed those found in modern oceans. These elements, with names like neodymium and ytterbium, play no known biological role. Yet their distribution patterns in ancient sediments reveal the circulation patterns of boring billion oceans. The slow accumulation of these elements in specific ocean basins provides evidence for the remarkably stable circulation patterns that characterize this quiet period. The temperature of the deep ocean remains surprisingly constant throughout the boring billion, hovering just a few degrees above freezing despite the gradually brightening sun and occasional changes in atmospheric composition. This thermal stability results from the efficient mixing of cold polar waters with the warmer waters from lower latitudes, creating a planetary refrigeration system that operates with the precision of a thermostat. The deep waters serve as a thermal reservoir that buffers the planet against climate changes that might otherwise destabilize the chemical equilibria that define this period. Metal sulfide minerals precipitate from these deep waters in patterns that create some of the most beautiful geological formations preserved from the boring billion. These deposits, rich in iron, copper, and zinc sulfides, form when metal-rich deep waters encounter sulfur compounds, creating layered mineral deposits that accumulate on the seafloor like geological artwork. The regular banding of these sulfide deposits reflects the stable chemical cycles that operate in the deep ocean, each layer representing another season's worth of precipitation from the planet's hidden chemical reactions. Scientists studying the chemistry of ancient seawater trapped in mineral deposits find themselves analyzing the molecular fossils of an ocean that existed in a fundamentally different chemical state than any modern sea. The very composition of these ancient waters tells stories of a planet where chemistry operated according to rules that have not applied for over 1 billion years, creating conditions that may never exist again in Earth's future. The irony of this deep ocean chemistry lies in its invisibility, vast reservoirs of chemical energy and biological potential hidden beneath waters that appear unchanged from the surface, supporting ecosystems and driving cycles that shape the entire planet's evolution while remaining forever unseen. In the quiet waters of shallow seas, where sunlight filters through liquid columns, undisturbed by complex predators or grazers, a revolution begins so subtle that it unfolds across hundreds of millions of years without leaving dramatic traces in the fossil record. The first eukaryotic cells organisms, whose genetic material lies enclosed within membrane-bound nuclei, emerge from the bacterial world through a process so gradual that the transformation itself becomes a study in evolutionary patience. These cells, perhaps 1,000 times larger than their bacterial ancestors, carry within their membrane-wrapped compartments the future potential of every plant, animal, and fungus that will ever exist. The origin of eukaryotic cells represents one of the most profound transitions in the history of life, yet it occurs during the boring billion with the same quiet persistence that characterizes all changes during this period. Unlike the dramatic evolutionary radiations that will mark later eons, the evolution of cellular complexity unfolds through incremental innovations, each one building upon previous developments so gradually that millions of years pass between significant advances. The very cells that will eventually give rise to redwood trees and blue whales first appear as microscopic organisms hardly distinguishable from their bacterial relatives, distinguished mainly by the internal membranes that divide their cellular contents into specialized compartments. These early eukaryotes developed through a process that scientists call endosymbiosis, the incorporation of one type of bacteria into another through partnerships that become so intimate they blur the boundaries between separate organisms. Bacteria that once lived independently begin residing permanently within larger cells, trading their freedom for the security of a protected environment and a steady supply of nutrients. Over millions of years, these bacterial residents evolve into specialized cellular organelles, their own DNA gradually transferring to their host's nucleus until they become integral components of a new kind of cellular architecture. The mitochondria that will eventually power all complex life first appear during the boring billion as free-living bacteria capable of using oxygen to extract energy from organic molecules. When these bacteria take up residence within larger cells, they bring with them the biochemical machinery necessary for aerobic respiration, the oxygen-burning metabolism that will make possible the energy-intensive lifestyles of all future multicellular organisms. Yet during the boring billion, when atmospheric oxygen levels remain low, these cellular powerhouses operate at reduced capacity, perhaps explaining why eukaryotic evolution proceeds so slowly during this period. Similarly, the chloroplasts that will enable plants to capture sunlight and transform it into chemical energy begin their evolutionary journey as cyanobacteria that become incorporated into eukaryotic cells. These photosynthetic partnerships create the first algae-simple organisms that combine the cellular complexity of eukaryotes with the solar-powered metabolism of cyanobacteria. The early algae of the boring billion remain microscopic and relatively simple, but they carry within their cellular architecture the potential for all future photosynthetic life, from single-celled diatoms to towering forests. The evolution of the eukaryotic nucleus itself remains one of biology's most intriguing mysteries, with fossils from the boring billion providing only tantalizing hints about how this cellular command center first developed. Some scientists propose that the nucleus evolved from an archaeal cell that engulfed various bacteria, while others suggest that internal membranes gradually subdivided bacterial cells into specialized compartments. Whatever the mechanism, the result is a new kind of cellular organization that allows much more sophisticated control over gene expression and cellular function. Perhaps most remarkably, the eukaryotic cells of the boring billion developed the molecular machinery for sexual reproduction, the process of genetic recombination that will become evolution's most powerful tool for generating biological diversity. Unlike the simple cell division that characterizes bacterial reproduction, sexual reproduction allows organisms to shuffle their genetic material with each generation, creating offspring that differ genetically from both parents. This innovation remains largely unexpressed during the boring billion, when stable environmental conditions provide little selective pressure for rapid genetic change, but it represents a crucial evolutionary development that will later enable life's explosive diversification. The cellular membranes of early eukaryotes develop increasing sophistication during these billion years, evolving specialized transport systems that allow precise control over which molecules enter and leave different cellular compartments. These membrane innovations enable eukaryotic cells to maintain much steeper chemical gradients than bacterial cells can achieve, creating the potential for more complex metabolisms and more efficient energy production. The development of sophisticated cellular membranes during the boring billion lays the groundwork for all future innovations in cellular physiology. Early eukaryotes also developed the first cytoskeleton's internal scaffolding systems made of protein fibers that give cells their shape and enable them to move in ways impossible for rigid-walled bacteria. These cytoskeletal systems allow eukaryotic cells to change shape, engulf food particles, and even move through their environment using temporary extensions of their cell membrane. The flexibility made possible by cytoskeletal systems will eventually enable some eukaryotic cells to abandon the sedentary lifestyle of bacteria and become active predators and grazers. The fossil record of early eukaryotes from the boring billion consists mainly of microscopic organic structures preserved in ancient sediment cell walls, resistant spores, and other durable cellular components that hint at the presence of more complex organisms. These microfossils, often only a few micrometers in diameter, represent some of the most important evidence for early eukaryotic evolution. Yet, they reveal relatively little about the sophisticated cellular processes that must have been developing during this time. DNA itself undergoes significant organizational changes within early eukaryotic cells, becoming associated with specialized proteins that help package the long genetic molecules into compact, manageable structures. This DNA packaging system enables eukaryotic cells to maintain much larger genomes than bacterial cells can handle, providing the genetic complexity necessary for multicellular development. The innovations in DNA organization that developed during the boring billion create the foundation for all future increases in biological complexity. The metabolism of early eukaryotes combines elements from all three domains of life: bacteria, archaea, and eukaryotes themselves, creating cellular biochemistry of unprecedented sophistication. These metabolic innovations allow eukaryotic cells to thrive in environmental conditions that would challenge simpler organisms. Yet, during the boring billion, they use these capabilities primarily to exploit the same ecological niches that bacteria have occupied for billions of years. Scientists studying the molecular evolution of eukaryotic cells find themselves reconstructing evolutionary events that occurred so gradually that millions of years separate each major innovation. Yet, the cumulative effect of these changes transforms life's potential in ways that will reshape the entire biosphere once environmental conditions become more favorable for complex organisms. The quiet irony of eukaryotic evolution during the boring billion lies in its timing. The most sophisticated cellular machinery in Earth's history develops during the period when life appears least innovative, creating biological potential that will remain largely unexpressed for hundreds of millions of years. The Moon hangs closer to Earth during these billion years, its gravitational embrace stronger than it will be in any future eon, pulling at the planet's waters with a force that creates tides unlike any that will surge across later shores. Each lunar month brings tide ranges that exceed modern extremes, drawing seawater hundreds of meters inland across the shallow continental margins, then retreating to expose vast mudflats that stretch toward horizons dotted with stromatolite reefs. These ancient shores experience tidal cycles that operate like planetary breathing, each rise and fall of the waters stirring nutrients through the shallow seas and preventing the stagnation that might otherwise characterize such a chemically stable period. The Earth itself spins faster during the boring billion, completing each rotation in perhaps 18 hours rather than the 24-hour days that will characterize later eons. This rapid spin, combined with the Moon's closer orbit, creates tidal forces that constantly reshape the planet's shallow marine environments. The stronger gravitational pull generates internal friction within Earth's oceans and solid body, gradually slowing the planet's rotation while pushing the Moon away through a process so gradual that it becomes imperceptible on any timescale shorter than millions of years. Yet this cosmic dance of gravitational energy transfer operates with such precision that it maintains stable orbital relationships throughout the billion-year duration of this quiet period. These powerful tides create some of the most dynamic environments available to life during an otherwise stable eon. Twice each day, vast areas of the continental shelves alternately flood and drain, creating zones where marine organisms must adapt to dramatic changes in water depth, salinity, and exposure to atmospheric conditions. The stromatolite communities that thrive in these intertidal zones develop remarkable tolerance for these environmental fluctuations, their bacterial constituents forming specialized layers that can withstand both submersion and aerial exposure with equal success. The tidal stirring of shallow seas during the boring billion prevents the development of the stagnant, oxygen-depleted bottom waters that might otherwise characterize such chemically quiet oceans. Instead, the constant movement of water masses ensures that nutrients remain in circulation, supporting the extensive stromatolite reefs that spread across the continental shelves. These tidal currents also transport dissolved chemicals between different marine environments, maintaining the chemical gradients that separate oxygenated surface waters from the anoxic depths. Along the ancient shorelines, tidal forces carve patterns in stone that will persist for billions of years as testimony to the moon's closer presence. Rhythmic sedimentary deposits called tidal rhythmites preserve the signature of these ancient tides in alternating layers of fine and coarse sediment, each pair representing a single tidal cycle. Modern geologists studying these rhythmite sequences can reconstruct not only the strength of ancient tides, but also the length of ancient days and months, reading Earth's rotational history in the stone record of its interaction with the Moon. The enhanced tidal mixing of the boring billion creates unique chemical environments where oxidized and reduced compounds meet in constantly shifting boundaries. These mixing zones become natural laboratories for chemical evolution, where molecules that rarely encounter each other in more stable environments can react to form new compounds. Some scientists speculate that the enhanced tidal activity of this period may have facilitated some of the biochemical innovations that characterize early eukaryotic evolution, providing the environmental turbulence necessary to drive complex chemical systems toward new configurations. Coastal erosion proceeds at accelerated rates under the influence of these powerful tides, grinding down the gradually rising mountain ranges and feeding vast quantities of sediment to the continental margins. This enhanced erosion contributes to the remarkable thickness of sedimentary sequences deposited during the boring billion, as the products of continental weathering accumulate in marine basins at rates that exceed those of most other geological periods. The constant reworking of coastal sediments by tidal action also contributes to the chemical stability of the oceans, ensuring that the products of rock weathering remain in circulation rather than accumulating in stagnant depositional environments. The Moon's gravitational influence extends beyond the oceans to affect the solid Earth itself, generating tidal bulges in the planet's rocky interior that create additional sources of internal heating. This tidal heating supplements the energy provided by radioactive decay within Earth's core and mantle, helping to maintain the convective processes that drive plate tectonics and volcanic activity. The enhanced tidal heating of the boring billion may contribute to the period's geological stability by providing just enough additional energy to keep the planet's internal processes operating smoothly without the dramatic fluctuations that characterize other eons. The stronger tidal forces also influence atmospheric circulation patterns, as the enhanced heating and cooling of tidal zones creates pressure differences that drive wind patterns different from those of later periods. These ancient wind systems help distribute heat and moisture around the planet, contributing to the climate stability that characterizes the boring billion. The regular daily cycle of tidal exposure and flooding creates predictable patterns of evaporation and condensation that influence local weather patterns along the extensive coastlines of this period. Perhaps most remarkably, the tidal cycles of the boring billion create temporal rhythms that may influence the evolution of biological clocks in early organisms. The strong, twice-daily pattern of environmental change provides clear timing cues that could help organisms coordinate their metabolic activities with external conditions. Some modern organisms still carry molecular clocks that seem calibrated to the shorter days and stronger tides of ancient Earth, suggesting that the enhanced tidal forces of the boring billion may have played a role in establishing some of life's most fundamental biological rhythms. The gravitational interaction between Earth and Moon during this period also affects the planet's axial tilt, helping to stabilize the orientation of Earth's rotational axis and contributing to the climate stability that allows chemical and biological systems to maintain their equilibria for hundreds of millions of years. Without this gravitational stabilization, Earth's climate might fluctuate more dramatically, disrupting the delicate balances that characterize the boring billion. Scientists studying the astronomical mechanics of the Earth-Moon system during this ancient period find themselves reconstructing gravitational relationships that operated according to the same physical laws that govern modern celestial mechanics, yet created environmental conditions unlike any that exist today. The mathematical precision of orbital mechanics, operating over timescales measured in billions of years, creates temporal patterns that influence everything from ocean chemistry to biological evolution. The ancient shores carved by these powerful tides preserve in stone the record of a gravitational relationship that will never again be quite so intimate. Each rhythmic layer, a fossilized day in a world where time itself moved to a different rhythm, where the moon's presence was felt more strongly in every surge and retreat of the restless seas. Even the planet's volcanic heartbeat settles into a quieter rhythm during these billion years, as if Earth itself has learned the value of moderation after the dramatic outbursts that characterized its more turbulent youth. The massive flood basalts that once covered entire continents with layers of molten rock kilometers thick fade into geological memory, replaced by a more restrained pattern of volcanic activity that builds islands and mountain ranges grain by grain rather than reshaping entire hemispheres in single eruptive episodes. This volcanic tranquility reflects deeper changes in the planet's thermal regime, as the gradual cooling of Earth's interior and the maturation of its convective systems create conditions that favor steady, moderate volcanic output over catastrophic eruptions. The volcanic processes of the boring billion operate like a planetary thermostat, releasing just enough heat and gas to maintain the chemical equilibria that characterize this stable period without triggering the dramatic environmental changes that more vigorous volcanism might cause. Mid-ocean ridges spread at steady rates, extruding fresh basalt that cools into new oceanic crust with the regularity of a geological metronome. These submarine volcanic systems operate largely invisible beneath the waves, their steady output contributing to the gradual separation of continental fragments while maintaining the chemical composition of seawater through the regular exchange of dissolved gases and minerals. Continental volcanism during this period tends towards smaller, more frequent eruptions that build volcanic edifices slowly through the accumulation of many modest lava flows rather than single massive outpourings. These volcanic systems develop over millions of years, each eruption adding another layer to growing volcanic mountains that rise gradually from the surrounding landscape. The lavas themselves often show evidence of slow cooling and gradual crystallization, creating rock textures that reflect the unhurried pace of volcanic processes during this quiet eon. The chemical composition of volcanic rocks from the boring billion reveals subtle changes in the planet's internal chemistry as Earth's mantle continues its slow evolution through billions of years of convective mixing. The gradual differentiation of the planet's interior concentrates certain elements in specific regions, creating mantle sources with distinct chemical signatures that will influence volcanic compositions for hundreds of millions of years. These chemical fingerprints, preserved in ancient lavas, provide scientists with indirect measurements of conditions deep within Earth's interior during this remote period. Volcanic gas emissions during the boring billion play a crucial role in maintaining the atmospheric equilibrium that characterizes this period. The steady release of carbon dioxide from volcanic sources balances the gradual removal of this greenhouse gas through rock weathering processes, creating a natural thermostat that helps maintain stable global temperatures despite the gradually brightening sun. Water vapor released by volcanic activity supplements the ocean's supply of this essential compound, while sulfur gases contribute to the complex atmospheric chemistry that regulates the planet's radiation balance. The timing of volcanic eruptions during this period appears remarkably regular when viewed across geological timescales, with major volcanic provinces developing in predictable patterns as the slowly moving continents pass over long-lived mantle plumes. These deep-seated thermal anomalies in Earth's interior create volcanic hotspots that remain stationary relative to the mantle while continents drift overhead, leaving chains of volcanic islands and seamounts that record the direction and rate of continental motion with the precision of geological surveying instruments. Perhaps most significantly, the moderate volcanic activity of the Boring Billion fails to trigger the massive environmental disruptions that volcanic episodes cause during other periods of Earth history. The absence of major flood basalt provinces during these billion years eliminates one of the primary drivers of mass extinction and rapid climate change, contributing to the biological and chemical stability that allows complex evolutionary processes to unfold gradually rather than being reset by periodic catastrophes. The volcanic islands that form during this period often develop into centers of biological innovation, as their isolated environments provide opportunities for organisms to experiment with new ecological strategies. The gradual emergence of volcanic islands from the deep ocean creates new habitats that can be colonized by early eukaryotic organisms, providing stepping stones for biological dispersal across the growing ocean basins. These volcanic environments also create unique chemical conditions where hydrothermal activity brings unusual combinations of dissolved minerals to the surface, potentially facilitating some of the biochemical innovations that characterize early complex cells. Hydrothermal systems associated with Boring Billion volcanism operate with the same steady persistence that characterizes all geological processes during this period. Hot springs and submarine hydrothermal vents provide localized environments where temperatures and chemical conditions differ dramatically from the surrounding landscape, creating ecological niches that support specialized communities of thermophilic bacteria. These hydrothermal environments serve as natural laboratories where high-temperature chemistry can produce unusual organic compounds that might otherwise be impossible to synthesize under normal surface conditions. The volcanic rocks deposited during the Boring Billion often show evidence of interaction with the stable atmospheric and oceanic systems of the period, developing distinctive weathering patterns and alteration products that reflect the unique chemical conditions of this time. These volcanic sedimentary interactions create new mineral assemblages that will persist in the geological record as testimony to the specific environmental conditions that characterize this quiet eon. Submarine volcanism during this period creates new seafloor topography that influences ocean circulation patterns and the distribution of marine organisms. Volcanic seamounts and ridges create barriers and channels that direct the flow of deep water currents, helping to maintain the stratified ocean structure that separates oxygenated surface waters from the anoxic depths. The gradual construction of these underwater volcanic features provides new surfaces for colonization by bacterial communities, expanding the habitat available to the simple organisms that dominate marine ecosystems during this period. The thermal energy released by volcanic processes during the Boring Billion contributes to the planet's overall energy budget in ways that help maintain the stable temperatures that characterize this period. Unlike the dramatic thermal pulses associated with major volcanic episodes in other eons, the steady heat release from Boring Billion volcanism provides a baseline level of thermal energy that supplements solar heating without causing disruptive temperature fluctuations, Scientists studying the volcanic record of the boring billion find themselves examining evidence for geological processes that operated with remarkable consistency across timescales that dwarf most other natural phenomena, creating conditions stable enough to support the gradual evolution of biological complexity while maintaining the chemical equilibria that define this most peaceful chapter in Earth's thermal history. The irony of this volcanic moderation lies in its effectiveness by restraining its own power. Earth's volcanic system creates conditions that allow other planetary processes to operate with unprecedented stability, demonstrating that sometimes the most profound influences arise from what does not happen, rather than from dramatic action. In the quiet depths where sunlight has never penetrated, simple multicellular organisms begin their first tentative experiments with cooperative living, building bodies that span multiple cells for the first time in Earth's history. These early multicellular pioneers remain microscopic, their bodies consisting of perhaps dozens or hundreds of cells organized into basic structures that hint at the architectural possibilities of cooperative biology. Unlike the dramatic explosion of multicellular diversity that will characterize later eons, these first experiments in cellular collaboration unfold with the same patient persistence that marks all innovation during the boring billion. Each evolutionary step separated by millions of years of gradual refinement. The transition from single-celled to multicellular life represents one of the most fundamental innovations in biological history, yet it occurs during the boring billion without fanfare or fossil drama. These early multicellular organisms leave few traces in the rock record, their soft bodies decomposing completely before they can be preserved as fossils. Only occasional impressions in fine-grained sediments and rare chemical signatures in ancient rocks hint at their existence, creating one of paleontology's most elusive chapters. The very simplicity that allows these organisms to pioneer multicellular living also makes them nearly invisible to future scientists trying to reconstruct their evolutionary innovations. The earliest multicellular organisms likely evolved from colonial microbes, single-celled organisms that live in closely associated groups but retain their individual identities. Over millions of years, these colonial associations become more integrated, with individual cells beginning to specialize for different functions within the group. Some cells might focus on reproduction, while others concentrate on obtaining nutrients or providing structural support. This division of labor, though simple by later standards, represents a revolutionary innovation that will make possible all future biological complexity. Cell-to-cell communication develops during this period as multicellular organisms evolve chemical signaling systems that allow different parts of their bodies to coordinate their activities. These early communication networks operate through simple chemical messengers that diffuse between adjacent cells, creating information pathways that enable multicellular bodies to function as integrated units rather than mere collections of individual cells. The molecular machinery for cellular communication that develops during the boring billion will later be elaborated into the sophisticated nervous and hormonal systems that characterize complex animals. The evolution of cellular adhesion during this period solves one of multicellular life's most basic challenges: how to keep cells attached to each other in the face of environmental forces that might tear multicellular bodies apart. Early multicellular organisms develop specialized proteins that act like molecular glue, creating strong but flexible bonds between adjacent cells. These adhesion systems must be sophisticated enough to hold multicellular bodies together while still allowing for growth, movement, and the controlled separation of cells during reproduction. Perhaps most remarkably, some early multicellular organisms begin to develop rudimentary forms of programmed cell death, the controlled elimination of specific cells to shape multicellular bodies or remove damaged components. This process, which seems counterintuitive from the perspective of individual cells trying to survive, becomes essential for multicellular development and maintenance. The evolution of programmed cell death during the boring billion represents a fundamental shift in biological organization, where the welfare of the multicellular organism takes precedence over the survival of individual cells. The metabolic innovations that support early multicellular life develop gradually through the patient accumulation of biochemical refinements. Multicellular organisms must solve new challenges related to nutrient distribution and waste removal. Since cells in the interior of multicellular bodies cannot directly exchange materials with the external environment, these early organisms likely develop simple circulation systems, perhaps just channels between cells that allow nutrients and waste products to move through multicellular bodies by diffusion. Reproduction in early multicellular organisms presents unique challenges that require new evolutionary solutions. Unlike single-celled organisms that can reproduce simply by dividing in half, multicellular organisms must develop mechanisms for creating new multicellular individuals from single cells. These reproductive innovations likely involve the development of specialized reproductive cells that carry the genetic information necessary to reconstruct the entire multicellular body plan in the next generation. The environmental conditions of the boring billion create ideal circumstances for these early experiments in multicellular living. The stable chemical conditions and relatively low levels of environmental stress allow multicellular organisms to evolve gradually without facing the extinction pressures that might eliminate such vulnerable early innovations. The predictable environments of this period provide the selective stability necessary for the slow development of complex multicellular traits. Early multicellular organisms also begin to explore the three-dimensional possibilities that become available when cells can be organized in space rather than being confined to single-cell architectures. These early explorations of multicellular geometry likely involve simple forms like hollow spheres, solid balls, or flat sheets of cells, each representing a different solution to the challenges of multicellular organization. The geometric principles established during these early experiments will later be elaborated into the vast diversity of body plans that characterize complex life. The oxygen levels of the boring billion, while low by modern standards, provide just enough of this reactive gas to support the enhanced metabolic demands of early multicellular organisms. The larger size and more complex organization of multicellular bodies require more energy than single-celled lifestyles, and the gradually increasing availability of oxygen creates conditions that can support these enhanced energy demands without providing so much oxygen that it becomes toxic to the still simple biochemistry of early multicellular life. Some early multicellular organisms may develop simple forms of behavior-coordinated responses to environmental stimuli that involve the integrated action of multiple cells. These behavioral innovations might include directed movement toward favorable conditions or coordinated responses to environmental threats. The development of multicellular behavior represents another fundamental innovation that will later be elaborated into the complex behavioral repertoires of advanced animals. The evolution of multicellular development, the process by which a single-celled embryo grows into a multicellular adult, likely begins during the boring billion, with simple developmental programs that control the division and differentiation of cells during growth. These early developmental systems must solve the fundamental challenge of how genetic information stored in DNA can be used to direct the construction of multicellular bodies with predictable shapes and cellular organizations. Scientists studying the origins of multicellular life find themselves trying to reconstruct evolutionary innovations that left virtually no direct fossil evidence, relying instead on molecular comparisons between modern organisms and theoretical models of early multicellular evolution to understand how these fundamental biological transitions occurred during Earth's most peaceful eon. The quiet irony of early multicellular evolution lies in its timing. Life's most fundamental organizational innovation develops during the period when biological innovation appears slowest, creating the cellular cooperation that will make possible all future biological complexity while remaining almost invisible in the geological record. The planet's climate system enters its own meditative rhythm during these billion years. As ice ages arrive and depart with astronomical precision, each glacial episode unfolding according to the slow orbital cycles that govern Earth's relationship with the Sun. These ancient ice ages operate on timescales that dwarf human comprehension, with individual glacial periods lasting millions of years and interglacial warmth stretching across equally vast intervals. Unlike the rapid climate oscillations that will characterize later eons, the ice ages of the boring billion advance and retreat with the patience of geological processes, their rhythms synchronized to the gravitational dance of planets and the gradual brightening of the solar furnace. The astronomical forcing mechanisms that drive these ancient glaciations operate through the same orbital cycles that influence climate throughout Earth's history: the gradual wobble of the planet's rotational axis, the slow changes in the shape of its orbital path around the Sun, and the periodic variations in the tilt of its rotational axis relative to the orbital plane. During the boring billion, these astronomical cycles create climate variations that unfold over timescales of tens of thousands to hundreds of thousands of years. Yet the overall pattern remains remarkably stable across the entire billion-year duration of this quiet period. When ice ages grip the planet during this time, they create conditions unlike any that will exist again in Earth's future. The lower atmospheric oxygen levels of the boring billion mean that ice sheets can advance into regions where the thin atmosphere provides little protection from ultraviolet radiation, creating frozen landscapes where only the most hardy bacterial communities can survive. These ice-covered continents reflect sunlight back to space with such efficiency that they help maintain the cold conditions that keep the ice sheets stable for millions of years at a time. The ice sheets themselves grow to enormous thickness during the prolonged glacial periods of the boring billion, accumulating layer upon layer of compressed snow that eventually transforms into ice kilometers thick. These vast accumulations of frozen water lock up significant portions of the planet's ocean water, lowering sea levels by hundreds of meters and exposing vast areas of the continental shelves. The exposed seafloor becomes a frozen wasteland where only the most specialized organisms can maintain active metabolisms in the permanently frozen ground. As these ice ages reach their maximum extent, they create feedback loops that help maintain the frozen conditions for geological periods. The high reflectivity of ice-covered surfaces reduces the amount of solar energy absorbed by the planet, while the lower sea levels expose more land area to the atmosphere, increasing the rate of rock weathering that removes carbon dioxide from the atmosphere. These feedback mechanisms operate so effectively during the boring billion that individual ice ages can persist for millions of years without significant fluctuation. The eventual retreat of these ice sheets occurs through equally gradual processes, as small changes in orbital cycles or atmospheric composition create warming trends that unfold over hundreds of thousands of years. As ice sheets begin to melt, the process accelerates through positive feedback loops. Darker surfaces exposed by melting ice absorb more solar energy, while rising sea levels reduce the land area available for carbon dioxide removing weathering processes. Yet even this deglaciation process operates with the measured pace that characterizes all climate changes during the boring billion. During interglacial periods, when the ice retreats to polar regions, global temperatures rise to levels that may exceed those of modern Earth. These warm periods create tropical conditions at high latitudes, allowing bacterial communities to colonize regions that remain frozen during glacial times. The enhanced warmth also accelerates the water cycle, increasing precipitation and creating more vigorous weather patterns that help distribute heat and moisture around the planet. These interglacial conditions can persist for millions of years, creating stable warm climates that last longer than entire ice ages in later periods. The ocean circulation patterns that develop during boring billion ice ages create unique chemical conditions that influence the entire planet's biogeochemical cycles. Cold, dense water formed near ice sheets sinks to the ocean depths, carrying dissolved gases and nutrients that help maintain the stratified ocean structure characteristic of this period. The slow circulation patterns that develop under glacial conditions ensure that deep water masses remain isolated from the surface for thousands of years, maintaining the chemical differences between oxygenated surface waters and anoxic depths. Perhaps most remarkably, the ice ages of the boring billion fail to trigger the mass extinctions that glacial periods cause during other eons. The simple bacterial communities that dominate life during this time prove remarkably resilient to climate change, with many species able to survive glacial conditions by entering dormant states or retreating to refugia near hydrothermal vents or other sources of geothermal heat. This biological resilience contributes to the overall stability that characterizes the period, allowing evolutionary innovations to accumulate gradually without being periodically reset by climate-driven extinctions. The chemical weathering of rocks during interglacial periods creates distinctive patterns of mineral alteration that reflect the unique atmospheric composition of the boring billion. The low oxygen levels mean that iron-bearing minerals weather differently than they do under modern atmospheric conditions, creating alteration products that preserve information about ancient atmospheric chemistry. These weathering signatures, preserved in paleosols and sedimentary deposits, provide some of the best evidence for the atmospheric conditions that existed during this remote period. The ice sheets of the boring billion also influence the planet's rotational dynamics, as the massive accumulations of ice at high latitudes change the distribution of mass around Earth's rotational axis. These changes affect the length of days and the stability of the planet's axial tilt, creating subtle influences on climate patterns that operate over timescales measured in millions of years. The gravitational effects of large ice sheets also influence tidal patterns, creating additional feedbacks between climate, orbital mechanics, and ocean circulation. Mountain glaciation during this period creates distinctive erosional landscapes where valley glaciers carve deep fjords and cirques into the gradually rising continental masses. These glacial erosional features develop over millions of years as ice streams flow slowly downslope, grinding away bedrock with the persistence of geological processes. The sediments produced by glacial erosion accumulate in marine basins, creating thick sequences of glacially derived sediments that preserve records of ice sheet fluctuations across multiple glacial cycles. Scientists studying the ice ages of the boring billion find themselves reconstructing climate systems that operated according to the same physical principles that govern modern glacial cycles, yet created environmental conditions that have no modern analogues, where astronomical forcing and atmospheric chemistry combine to produce glacial rhythms of unprecedented duration and stability. The distant echo of these ancient ice ages whispers through deep time, each glacial cycle a breath in the planet's billion-year meditation, each warming and cooling phase a note in the orbital symphony that governed Earth's climate during its most peaceful geological era. The very minerals that compose Earth's crust undergo a quiet revolution during these billion years, as the planet's gradually oxygenating surface creates chemical conditions that allow new crystalline forms to develop with the patience of geological time. More than half of all known mineral species owe their existence to the oxygen-rich environments that first become widespread during and after the boring billion. Yet this mineral evolution unfolds so gradually that individual species appear and stabilize across timescales measured in millions of years. The rocks themselves become laboratories where atoms experiment with new arrangements, creating colors and crystal structures that had never existed in the reducing atmosphere of Earth's early history. Iron minerals undergo the most dramatic transformations during this period, as the availability of atmospheric oxygen allows this abundant metal to form oxidized compounds that paint the landscape in shades of red, yellow, and brown that were impossible under earlier atmospheric conditions. Hematite and goethite iron oxide minerals that create the rusty colors of oxidized iron begin to form in surface environments where iron-bearing rocks weather under the influence of oxygen-rich groundwater. These iron oxides accumulate in sedimentary deposits that will preserve the chemical signature of the boring billion's unique atmospheric composition for billions of years. The formation of new iron minerals during this period creates some of the most beautiful geological formations preserved from ancient Earth. Banded iron formations, those distinctive layered rocks that alternate between iron-rich and silica-rich bands, largely disappear from the geological record during the boring billion as ocean chemistry stabilizes and iron precipitation becomes less dramatic. Instead, iron minerals begin forming in terrestrial environments where weathering processes concentrate iron in soils and sediments, creating the red beds and iron-rich paleosols that characterize many boring billion sedimentary sequences. Copper minerals, too, begin their own evolutionary journey during this time, as the oxidizing conditions allow copper to form the brilliant blue and green compounds that make this metal one of geology's most colorful elements. Malachite and azurite copper carbonate minerals that display stunning shades of green and blue first appear in significant quantities during the boring billion, forming in oxidized zones around copper deposits where meteoric water carries dissolved oxygen deep into the Earth's crust. These copper minerals create some of the most striking colors in the mineral kingdom. Their brilliant hues are a direct result of the atmospheric changes that characterize this period. The evolution of clay minerals during the boring billion reflects the changing chemistry of weathering processes as atmospheric composition stabilizes and continental weathering patterns become more predictable. New types of clay minerals form as feldspars and other common rock-forming minerals break down under the influence of slightly acidic rainwater and groundwater. These clay minerals accumulate in thick sequences of mudstone and shale that preserve detailed records of ancient weathering conditions, their crystal structures encoding information about temperature, humidity, and atmospheric composition during their formation. Sulfate minerals begin to diversify during this period as the oxidation of sulfur-bearing compounds creates new opportunities for sulfate formation in surface environments, gypsum and anhydrite calcium. Sulfate minerals that form when sulfate-rich waters evaporate become more common in evaporate deposits as marine chemistry stabilizes and creates conditions favorable for sulfate precipitation. These sulfate minerals often form beautiful crystals that preserve delicate records of ancient seawater chemistry and evaporation conditions, perhaps most significantly. The boring billion witnesses the first widespread formation of secondary uranium minerals, brightly colored compounds that form when uranium-bearing rocks weather under oxidizing conditions. These uranium minerals, with their distinctive yellow and green colors, create some of the most radioactive mineral deposits on Earth, their formation made possible only by the availability of atmospheric oxygen to oxidize uranium from its reduced, relatively immobile form to its oxidized, highly mobile form. The appearance of secondary uranium minerals in the geological record provides some of the best evidence for the timing and extent of atmospheric oxygenation during this period. The formation of new manganese minerals during the boring billion creates another distinctive signature of the period's unique chemical conditions. Manganese oxides, which form striking black and metallic gray minerals, begin to precipitate from seawater and groundwater as oxygen levels rise sufficiently to oxidize dissolved manganese. These manganese minerals often form intricate dendritic patterns that resemble fossilized plants or lightning bolts, their growth controlled by the diffusion of dissolved manganese through oxygen-rich waters. Carbonate minerals undergo subtle but important changes during this period as atmospheric carbon dioxide levels stabilize and marine chemistry reaches new equilibria. The formation of different carbonate minerals, calcite, aragonite, and dolomite, becomes more predictable as ocean temperature and chemistry stabilize, creating carbonate deposits with distinctive textures and compositions that reflect the unique marine conditions of the boring billion. These carbonate minerals often preserve exquisite details of ancient marine environments, including the structures built by stromatolite-forming bacterial communities. The weathering of volcanic rocks during the boring billion creates distinctive alteration mineral assemblages that reflect the unique atmospheric conditions of the period. Zeolite minerals, complex hydrated aluminosilicates that form when volcanic glass reacts with groundwater, develop in patterns that preserve information about groundwater chemistry and circulation patterns. These zeolite minerals often display beautiful crystal forms and create some of the most scientifically interesting mineral deposits from this period. Phosphate minerals begin to diversify during the boring billion, as the cycling of phosphorus through marine environments creates new opportunities for phosphate precipitation. Apatite and other phosphate minerals form in marine sediments where phosphorus-rich waters become supersaturated with respect to phosphate compounds. These phosphate minerals often preserve organic matter and cellular structures with exceptional fidelity, creating some of the best preserved microfossils from this ancient period. The formation of new silicate minerals during this time reflects the changing chemistry of hydrothermal systems as atmospheric composition influences the chemistry of groundwater and surface water that interacts with hot rocks. These hydrothermal silicate minerals often display unusual chemical compositions and crystal structures that record the specific pressure, temperature, and chemical conditions under which they formed. Scientists studying the mineral evolution of the boring billion find themselves examining crystalline archives that preserve information about atmospheric chemistry, ocean composition, and weathering processes with molecular precision. Each mineral species a chemical fossil that records the specific environmental conditions that made its formation possible. The quiet beauty of this mineral evolution lies in its subtlety, new colors and crystal forms appearing grain by grain in rocks around the world, creating a planetary palette that reflects the chemical maturation of Earth's surface systems during its most peaceful billion years. The carbon cycle settles into its most meditative rhythm during these billion years, moving this essential element between atmosphere, ocean, and rock with the steady pulse of a planetary heartbeat that will persist virtually unchanged across timescales that dwarf the existence of entire species. Carbon dioxide dissolves into rainwater and seawater, reacts with weathering rocks to form bicarbonate ions, flows through groundwater and river systems to the ocean, precipitates as carbonate minerals in marine sediments, and returns to the atmosphere through volcanic outgassing, each step in this cycle operating with such regularity that the planet's carbon budget remains balanced within narrow limits for hundreds of millions of years. This carbon cycle operates as Earth's primary climate regulation system, automatically adjusting atmospheric greenhouse gas concentrations in response to changes in solar luminosity, volcanic activity, and biological productivity. When volcanic outgassing increases atmospheric carbon dioxide levels, enhanced greenhouse warming accelerates rock weathering, which removes more carbon dioxide from the atmosphere through chemical reactions with silicate minerals. When atmospheric carbon dioxide decreases, reduced greenhouse warming slows weathering rates, allowing volcanic outgassing to gradually restore atmospheric carbon dioxide levels. This negative feedback system operates with such precision during the boring billion that global temperatures remain stable despite the sun's gradually increasing brightness. The ocean's role in this carbon cycle becomes increasingly sophisticated during the boring billion, as the stratified water column creates distinct carbon reservoirs with different chemical properties and residence times. Surface waters exchange carbon dioxide rapidly with the atmosphere, maintaining chemical equilibrium with atmospheric concentrations over timescales of months to years. But deep waters, isolated from atmospheric contact by the stable density stratification that characterizes boring billion oceanography, maintain carbon concentrations that reflect atmospheric composition from hundreds or thousands of years earlier. This ocean carbon storage system creates a vast buffer that helps stabilize atmospheric carbon dioxide concentrations against short-term fluctuations. The biological component of the carbon cycle operates with the same steady persistence that characterizes all biological processes during this period. Stromatolite-building cyanobacteria fix atmospheric carbon dioxide into organic compounds through photosynthesis, but they do so at rates that remain virtually constant across millions of years. Unlike the dramatic fluctuations in biological productivity that characterize later eons, the biological carbon cycle of the boring billion maintains steady rates of organic carbon production and decomposition that contribute to the overall chemical stability of the period. Carbonate precipitation in marine environments during the boring billion follows patterns that reflect the unique chemistry of this period's oceans. The relatively low atmospheric carbon dioxide levels create seawater that is supersaturated with respect to carbonate minerals, promoting the precipitation of limestone and dolomite in shallow marine environments. This carbonate precipitation removes carbon from the ocean atmosphere system and buries it in sedimentary rocks where it will remain sequestered for hundreds of millions of years. The steady rate of carbonate burial during this period helps maintain atmospheric carbon dioxide at levels that support stable greenhouse warming. The weathering of silicate rocks during the boring billion operates as the primary mechanism for removing carbon dioxide from the atmosphere. Yet this process unfolds so gradually that individual weathering reactions may take thousands of years to complete. Rainwater, slightly acidified by dissolved carbon dioxide, reacts with feldspar and other silicate minerals to produce clay minerals, dissolved ions, and bicarbonate that eventually reaches the ocean. This weathering process consumes atmospheric carbon dioxide and helps regulate global temperature, operating more efficiently as temperatures rise and more slowly as temperatures fall. Organic carbon burial during this period follows different patterns than in later eons, as the absence of complex multicellular organisms means that most organic matter consists of simple bacterial remains and dissolved organic compounds. The anoxic conditions that prevail in deep marine environments help preserve organic carbon from complete decomposition, allowing significant quantities of this material to be buried in sediments where it removes carbon from the active carbon cycle. This organic carbon burial represents one of the primary mechanisms for maintaining atmospheric oxygen levels during the boring billion. The isotopic composition of carbon during this period provides scientists with detailed information about the operation of ancient carbon cycles. Carbon isotopes record the balance between organic and inorganic carbon burial, the efficiency of photosynthesis by marine organisms, and the relative importance of different carbon cycle processes. The remarkably stable carbon isotopic signatures preserved in boring billion rocks testify to the consistent operation of carbon cycle processes across hundreds of millions of years. Hydrothermal carbon cycling during this period operates through interactions between seawater and hot volcanic rocks at mid-ocean ridges and other hydrothermal systems. These high-temperature reactions alter the carbon chemistry of seawater and influence the global carbon budget, yet they do so at steady rates that contribute to, rather than disrupt, the overall stability of the carbon cycle. Hydrothermal systems also provide carbon compounds that support specialized bacterial communities in the deep ocean, creating additional pathways for carbon cycling that operate independently of photosynthesis. The carbon cycle's interaction with other biogeochemical cycles during the boring billion creates complex feedback loops that help maintain planetary chemical stability. The cycling of phosphorus and nitrogen influences biological productivity, which affects organic carbon burial rates. The cycling of sulfur influences the chemistry of marine sediments, which affects carbonate precipitation. The cycling of iron influences ocean chemistry, which affects carbon dioxide solubility. All these cycles operate in coordination during the boring billion, creating a planetary chemical system of unprecedented stability. Continental carbon storage during this period develops through the accumulation of thick sedimentary sequences that lock up carbon in both carbonate minerals and organic matter. These continental carbon reservoirs grow steadily throughout the boring billion, representing vast stores of carbon that will remain sequestered until future tectonic processes expose them to weathering or metamorphism. The steady growth of these carbon reservoirs helps maintain atmospheric carbon dioxide at levels compatible with stable climate conditions. Perhaps most remarkably, the carbon cycle of the boring billion operates without triggering the dramatic climate oscillations that carbon cycle perturbations cause during other periods of Earth history. The gradual, steady operation of all carbon cycle processes creates conditions where the climate system can respond smoothly to external forcing without experiencing the rapid transitions or unstable fluctuations that characterize more dynamic periods. Scientists studying the carbon cycle of the boring billion find themselves examining a biogeochemical system that operated with clockwork regularity across timescales that challenge human comprehension, maintaining planetary chemical equilibria through the steady operation of processes that will never again achieve such remarkable stability in Earth's future history. The profound patience of this ancient carbon cycle whispers through the geological record like a planetary meditation on the theme of chemical balance, each carbon atom cycling between reservoirs according to rhythms measured in millions of years, each molecular transformation contributing to the maintenance of conditions that allowed life to experiment quietly with complexity during Earth's most peaceful eon. Beneath the planet's surface waters, in the quiet darkness of anoxic environments where oxygen has never penetrated, life continues its patient experiments with innovations that will remain hidden for hundreds of millions of years before transforming the entire biosphere. Sexual reproduction emerges during these billion years as one of evolution's most revolutionary inventions. Yet it develops so gradually and operates so subtly that its presence becomes detectable only through the molecular archaeology of modern genetics. This biological innovation, which will eventually become the primary driver of evolutionary diversity, begins as a simple mechanism for exchanging genetic material between individual cells, allowing organisms to shuffle their hereditary information in ways that create offspring genetically distinct from either parent. The evolution of sexual reproduction during the boring billion represents a fundamental shift in how life approaches the challenge of genetic variation. For billions of years, organisms had relied primarily on random mutations to generate the genetic diversity necessary for evolutionary adaptation. Sexual reproduction introduces an entirely new source of variation by allowing organisms to recombine existing genetic material in novel ways, potentially generating thousands of different genetic combinations from a single pair of parents. This innovation multiplies the rate at which evolution can explore new biological possibilities, though during the stable conditions of the boring billion, this enhanced evolutionary potential remains largely unexpressed. The molecular machinery that makes sexual reproduction possible develops through the gradual evolution of cellular systems for DNA repair, recombination, and accurate chromosome segregation. These processes require unprecedented precision in cellular mechanics, as organisms must be able to duplicate their entire genetic contents, exchange portions of DNA between chromosomes, and then distribute the resulting genetic material accurately to reproductive cells. The evolution of this molecular machinery during the boring billion represents one of the most sophisticated achievements in cellular engineering, requiring the coordinated evolution of dozens of different protein systems. Meiosis, the specialized cell division process that produces reproductive cells with half the normal chromosome number, emerges during this period as perhaps the most complex cellular process that had evolved up to that point in Earth's history. This process must solve the intricate choreography of pairing homologous chromosomes, exchanging genetic material between them through crossing over, and then separating them accurately into reproductive cells. The precision required for meiosis to operate successfully represents a quantum leap in cellular sophistication that will make possible all future advances in multicellular complexity. The development of distinct sexes during the boring billion creates new forms of biological cooperation and specialization that operate at the level of entire organisms rather than individual cells. Some organisms begin to specialize as producers of small, mobile reproductive cells, while others focus on creating large, nutrient-rich reproductive cells that can support early development. This reproductive division of labor, though simple in its early forms, establishes the foundation for all future sexual dimorphism and reproductive strategies. Genetic recombination mechanisms evolve during this period to become increasingly sophisticated, allowing organisms to exchange genetic material with greater precision and control. Early recombination systems may have operated relatively randomly, but over millions of years they evolve regulatory mechanisms that can control where and when genetic exchange occurs. These innovations in genetic recombination will eventually become essential tools for generating the genetic diversity necessary to support complex multicellular development and immune system function. The evolution of reproductive isolation mechanisms during the boring billion begins the process that will eventually lead to the formation of distinct species. As organisms develop increasingly sophisticated reproductive systems, they also evolve mechanisms that prevent successful reproduction with genetically distant relatives. These reproductive barriers, though primitive during the boring billion, represent the first steps toward the biological species concept that will become fundamental to understanding biodiversity in later eons. Cellular recognition systems developed during this period to allow organisms to distinguish between their own cells and foreign cells, laying the groundwork for the immune systems that will become essential for multicellular life. These early recognition systems operate through surface proteins that can identify chemical signatures characteristic of the organism's own genetic background. The evolution of these cellular recognition systems represents another crucial innovation that makes possible both sexual reproduction and the cellular cooperation necessary for multicellular development. The timing mechanisms that coordinate sexual reproduction evolved to become increasingly sophisticated during the boring billion, allowing organisms to synchronize their reproductive activities with environmental conditions or with other individuals of their species. These biological clocks, operating through molecular oscillators that can measure time with remarkable precision, enable organisms to coordinate complex reproductive behaviors that require precise temporal coordination between multiple individuals. Gamete formation. During this period involves the evolution of specialized cellular differentiation programs that can transform ordinary somatic cells into highly specialized reproductive cells. These differentiation programs must be able to activate entirely different sets of genes, modify cellular structure and metabolism, and prepare cells for the unique challenges of reproduction and early development. The complexity of these cellular reprogramming systems represents another major innovation in cellular control mechanisms. The biochemical innovations that support sexual reproduction during the Boring Billion include the evolution of specialized enzymes for DNA recombination, proteins for chromosome pairing and segregation, and signaling molecules for coordinating reproductive activities. Many of these molecular systems operate with extraordinary precision, requiring error rates lower than 1 mistake per billion molecular interactions. The evolution of such high-fidelity molecular machinery represents a remarkable achievement in biological engineering. Horizontal gene transfer. The direct exchange of genetic material between organisms that are not in a reproductive relationship continues to operate during the Boring Billion, but becomes increasingly regulated as organisms evolve more sophisticated genetic systems. The balance between vertical inheritance through reproduction and horizontal transfer through other mechanisms creates opportunities for rapid evolutionary innovation while maintaining genetic stability within lineages. The energetic costs of sexual reproduction create new selective pressures during the Boring Billion, as organisms must evolve metabolic systems capable of supporting the energy-intensive processes of meiosis, gamete formation, and reproductive behavior. These energetic demands may explain why sexual reproduction evolves slowly during this period, as the stable environmental conditions provide little immediate advantage to compensate for its metabolic costs. Scientists studying the evolution of sexual reproduction during the Boring Billion find themselves reconstructing biological innovations that left virtually no direct fossil evidence, relying instead on comparative molecular biology and theoretical models to understand how these fundamental reproductive mechanisms first evolved during Earth's most peaceful eon. The hidden revolution of sexual reproduction during the Boring Billion operates like a biological encryption system, encoding within cellular machinery the potential for evolutionary explosions that will not be expressed until environmental conditions become more challenging, creating biological innovations that remain dormant for hundreds of millions of years before reshaping the entire trajectory of life on Earth. Earth's magnetic field begins its own slow wandering during these billion years, as the planet's magnetic poles drift across the surface according to processes deep within the molten iron core that operate on timescales measured in hundreds of thousands of years. Unlike the relatively rapid magnetic reversals that characterize other periods of Earth's history, the magnetic field of the Boring Billion maintains longer periods of stable polarity, with the north and south magnetic poles remaining in roughly the same orientation for millions of years at a time before slowly migrating to new positions. This magnetic stability contributes to the overall tranquility of the period, providing consistent protection from cosmic radiation that helps maintain the chemical and biological equilibria that define these quiet billion years. The generation of Earth's magnetic field through the motion of liquid iron in the planet's outer core operates according to the same basic principles throughout geological time. Yet, the specific patterns of convection and magnetic field production show subtle variations that reflect the gradually changing thermal structure of the planet's interior. During the Boring Billion, the core cools slowly from its initial formation heat, while radioactive decay within the mantle and core provides a steady source of thermal energy that drives the convective motions responsible for magnetic field generation. This thermal evolution creates magnetic field patterns that are neither as chaotic as those of Earth's early history, nor as complex as those that will characterize later periods. The magnetic field lines that emanate from Earth's core and extend into space create a protective magnetosphere that deflects most of the charged particles streaming from the Sun in the solar wind. During the boring billion, this magnetic shielding operates with remarkable consistency, maintaining protection levels that allow atmospheric chemistry to evolve gradually without the disruptions that more variable magnetic fields might cause. The stable magnetosphere also helps preserve the planet's atmosphere against erosion by solar wind particles, ensuring that atmospheric composition can maintain its delicate balances over geological timescales. Magnetic field intensity during this period fluctuates within relatively narrow bounds, maintaining field strengths that are comparable to modern values but showing less dramatic variation than will characterize later eons. The steady magnetic field intensity reflects the stable thermal regime within Earth's core, where heat production and heat loss remain approximately balanced across hundreds of millions of years. This thermal stability allows the dynamo processes that generate the magnetic field to operate in a relatively steady state, producing magnetic field patterns that change slowly and predictably. The recording of ancient magnetic field directions in volcanic rocks and sediments during the boring billion creates one of the most complete archives of magnetic field behavior preserved from any period of Earth history. These paleomagnetic records reveal magnetic field directions that slowly migrate across the planet's surface as the magnetic poles wander in response to changes in core convection patterns. The gradual nature of these magnetic changes during the boring billion contrasts sharply with the rapid magnetic reversals that punctuate other periods, creating paleomagnetic records that show smooth, continuous evolution rather than abrupt transitions. Continental drift during the boring billion can be reconstructed with unusual precision using paleomagnetic data, as the stable magnetic field provides a reliable reference frame for determining the ancient positions and orientations of continental landmasses. The magnetic signatures preserved in rocks from this period reveal the slow separation of continental fragments and their gradual drift across the planet's surface at rates of a few centimeters per year. These paleomagnetic reconstructions provide some of the most detailed records of ancient continental positions available from the Precambrian era. The interaction between Earth's magnetic field and the solar wind during the boring billion creates auroral displays that may have been more stable and predictable than those of later periods. The consistent magnetic field geometry and steady solar wind conditions of this time could have produced auroral patterns that persisted for thousands of years without significant change, creating atmospheric light shows of unprecedented regularity. These ancient auroras, though unobserved by any life form capable of appreciating their beauty, represent another manifestation of the cosmic harmony that characterizes this peaceful period. Magnetic field variations during the boring billion may have influenced the evolution of early life by providing stable conditions for the development of biological systems that are sensitive to magnetic fields. Some modern bacteria can navigate using Earth's magnetic field through specialized organelles called magnetosomes that contain magnetic minerals. The stable magnetic conditions of the boring billion may have provided ideal circumstances for the evolution of such magnetic sensing systems, allowing early organisms to develop sophisticated navigation capabilities that operate on planetary scales. The magnetic properties of rocks formed during the boring billion preserve detailed records of ancient magnetic field behavior that provide scientists with information about conditions deep within Earth's interior during this remote period. The magnetic minerals that crystallize in volcanic rocks align themselves with the ambient magnetic field at the time of formation, creating permanent records of magnetic field direction and intensity that can be measured billions of years later. These paleomagnetic archives represent some of the most direct evidence available for the operation of Earth's deep interior systems during the Precambrian. Magnetic field reversals during the boring billion occur much less frequently than during other periods, with individual polarity intervals lasting millions of years rather than the thousands of years typical of more recent magnetic history. This reduced reversal frequency reflects the stable thermal conditions within Earth's core, where the convective processes that drive magnetic field generation operate in more regular patterns than during periods of more vigorous internal activity. The long polarity intervals of the boring billion create magnetic field conditions that remain virtually unchanged across the entire evolutionary history of early complex organisms. The magnetic declination and inclination, the horizontal and vertical components of magnetic field direction, show gradual, systematic changes during the boring billion that reflect the slow evolution of magnetic field geometry as core convection patterns evolve. These changes occur so slowly that they are imperceptible on biological timescales, yet they create long-term trends in magnetic field behavior that persist across geological eras. The systematic nature of these magnetic changes during the boring billion contrasts with the more chaotic magnetic behavior that characterizes other periods. Secular variation. The slow drift of magnetic field direction that occurs even during periods of stable polarity operates during the boring billion, at rates that are measurably slower than those of later periods. This reduced secular variation reflects the stable core processes that characterize this period, creating magnetic field patterns that change so gradually they provide reliable navigational references for millions of years at a time. The predictability of magnetic field behavior during this period may have contributed to the overall environmental stability that allowed gradual evolutionary innovations to accumulate without disruption. Scientists studying the magnetic field history of the boring billion find themselves examining records of one of Earth's most fundamental physical systems operating in its most stable configuration, creating magnetic field patterns that provide both protection for surface processes and reliable archives of deep Earth behavior during the planet's most tranquil geological period. The magnetic wandering of this ancient time whispers through the paleomagnetic record like a compass needle searching for true north across geological time. Each slow migration of the magnetic poles, another note in the planetary symphony of forces that maintained Earth's stability during its billion-year meditation. The boring billion draws toward its close as subtle chemical changes begin to stir in the ocean depths, preparing the stage for transformations that will eventually end this longest period of stability in Earth's history. Around 800 million years ago, the first hints of change appear in the form of slightly rising oxygen levels and small fluctuations in the isotopic composition of marine sulfur, as if the planet's chemical systems are beginning to wake from their billion-year equilibrium. These early signals of instability remain almost imperceptible, detectable only through the most sensitive geochemical measurements, yet they mark the beginning of the end for the remarkable stability that has characterized this quiet eon. The mechanisms that trigger the end of the boring billion remain among geology's most intriguing mysteries, with scientists proposing various scenarios involving changes in continental configuration, evolution of new biological processes, or subtle shifts in the planet's thermal regime. Perhaps the gradual cooling of Earth's interior finally reaches a threshold that alters mantle convection patterns, changing the rate of volcanic outgassing and disturbing the atmospheric equilibrium that has persisted for so long. Or maybe the slow evolution of eukaryotic organisms finally produces biological innovations sophisticated enough to begin altering marine chemistry in measurable ways. The first clear signs of change appear in the carbon isotope record around 850 million years ago, when the stable carbon cycle that has operated unchanged for hundreds of millions of years begins to show small but systematic variations. These isotopic fluctuations suggest changes in the balance between organic carbon burial and carbonate precipitation, indicating that the biological and chemical processes that regulate atmospheric composition are beginning to operate differently. The carbon cycle disturbances remain modest compared to those that will characterize later periods, but they represent the first cracks in the chemical stability that has defined the boring billion. Ocean chemistry begins to show signs of instability around the same time, as the stratified water column that has maintained its chemical gradients for hundreds of millions of years starts to experience more vigorous mixing. This enhanced circulation may result from changes in continental configuration as the fragments of the former supercontinent Columbia begin to reassemble into the new supercontinent Rodinia. The changing patterns of ocean circulation alter the distribution of nutrients and dissolved gases, creating new chemical environments that will provide opportunities for biological innovation. The rise in atmospheric oxygen levels that eventually ends the boring billion begins so gradually that millions of years pass before the change becomes clearly detectable in the geological record. This oxygenation may result from evolutionary innovations in photosynthetic organisms that increase their efficiency, or from changes in ocean circulation that reduce the burial of organic carbon and allow more oxygen to accumulate in the atmosphere. Whatever the cause, rising oxygen levels begin to transform marine chemistry in ways that will make possible the explosive evolution of complex multicellular life. Phosphorus cycling shows some of the earliest signs of systematic change as the boring billion draws to a close, with enhanced weathering of continental rocks beginning to deliver larger quantities of this essential nutrient to marine environments. The increased phosphorus supply may result from climate changes associated with continental reassembly, or from the evolution of new biological processes that enhance the weathering of phosphorus-bearing minerals. This enhanced nutrient supply creates conditions that can support higher levels of biological productivity than have been possible during the nutrient-limited conditions of the boring billion. The first appearances of more complex eukaryotic fossils in the geological record around 750 million years ago signal that the biological innovations that have been developing gradually during the boring billion are finally beginning to express themselves in observable ways. These early complex organisms remain simple by later standards, but they represent a significant increase in biological sophistication compared to the bacterial and simple eukaryotic communities that have dominated marine ecosystems for the previous billion years. Magnetic field behavior begins to show increasing variability as the boring billion ends, with shorter polarity intervals and more frequent reversals indicating changes in core convection patterns. This increased magnetic instability may reflect thermal evolution within Earth's interior or changes in the planet's rotational dynamics associated with continental reassembly. The less stable magnetic field provides less consistent protection from cosmic radiation, potentially contributing to increased mutation rates that accelerate biological evolution. Climate systems show the first signs of increased variability as atmospheric composition begins to change and continental positions shift toward the Rodinia configuration. The climate stability that has characterized the boring billion begins to give way to more dynamic conditions that will eventually lead to the extreme glaciations of the Neoproterozoic era. These early climate changes remain subtle, but they represent the beginning of the environmental instability that will drive rapid evolutionary innovation in the periods that follow. The gradual breakdown of the chemical and biological equilibria that have defined the boring billion creates positive feedback loops that accelerate the pace of change. Rising oxygen levels promote more efficient biological productivity, which further increases oxygen production. Enhanced nutrient cycling supports larger and more complex biological communities, which in turn affect ocean chemistry in ways that promote additional change. These feedback mechanisms transform the gradual changes that mark the end of the boring billion into the accelerating transformations that will characterize the Neoproterozoic era. Perhaps most significantly, the cellular innovations that have been accumulating gradually during the boring billion begin to interact in ways that create entirely new biological possibilities. The combination of sexual reproduction, multicellular development, and enhanced cellular metabolism reaches a threshold of sophistication that enables organisms to exploit environmental opportunities that have been unavailable to simpler life forms. This biological revolution, made possible by the patient accumulation of innovations during the stable conditions of the boring billion, will eventually transform the entire biosphere. The volcanic record shows subtle but systematic changes as the boring billion ends, with slightly increased levels of volcanic activity and changes in the composition of volcanic gases. These volcanic changes may reflect the thermal and chemical evolution of Earth's interior, or they may result from the tectonic processes associated with supercontinent assembly. Whatever their cause, these volcanic changes contribute to the atmospheric and oceanic chemistry changes that mark the end of this stable period. Scientists studying the end of the boring billion find themselves examining one of Earth's most fundamental transitions, when a planetary system that had operated in stable equilibrium for 1 billion years begins to evolve toward the more dynamic conditions that will characterize all subsequent Earth history. The end of this quiet eon approaches like dawn after the longest night, with the first subtle stirrings of change creating conditions that will eventually wake the planet from its billion-year sleep and set the stage for life's greatest evolutionary experiments. The billion years fade into deep geological rest, their quiet chapters closing like the final pages of Earth's longest meditation. In the settled sediments of ancient seas, in the layered limestone built grain by patient bacteria, in the iron-rich bands that painted the seafloor in rust and ochre, the boring billion leaves its gentle signature written in stone. The planet holds its breath one last time before the great stirring that will follow, before oxygen rises and ice advances, and life discovers the explosive possibilities hidden within cellular cooperation. But here, in this moment, suspended between deep time and deeper time, Earth rests in the profound stillness it has earned through 1,000 million years of chemical harmony. The stromatolites continue their ancient work in shallow seas that have known no predators, no grazers, only the endless patience of bacterial communities building their limestone cities layer by microscopic layer. The continents drift slowly apart and slowly together again, their mountain ranges rising and eroding with geological discretion, their weathering contributing to the carbon cycle's steady pulse. Somewhere in the ocean depths, eukaryotic cells carry their hidden innovations like seeds waiting for spring, their nuclei wrapped in membranes, their mitochondria breathing softly in the low oxygen waters, their genetic machinery prepared for the sexual reproduction that will someday reshape evolution itself. The planet's magnetic field wanders slowly across the surface, protecting the thin atmosphere that maintains its delicate chemical balances with the precision of a master craftsman. The eon ends not with drama, but with the same quiet persistence that has characterized every moment of these billion years. Changes stir so gradually that mountains could rise and fall between the first stirring and its expression in the geological record. Ice ages approach with astronomical patience, their rhythms synchronized to orbital cycles that measure time in units too vast for any living consciousness to comprehend. In the deep time that stretches ahead, Complex life will explode across the planet in forms beyond imagination. Animals will swim and crawl and fly. Plants will colonize the land. Ecosystems will develop complexities that make the simple bacterial mats of the boring billion seem like whispered rumors of life's potential. But all of it, every flower that will bloom and every creature that will breathe, will owe its existence to the quiet innovations that accumulated during these billion patient years. When Earth learned the most profound lesson of all, that the greatest transformations arise not from sudden change, but from simple processes repeated with the persistence of stone. The boring billion settles into the geological record like sediment in still water, each moment of its vast duration adding another layer to the foundation upon which all future complexity will rest. Sleep comes to this ancient world not as an ending, but as preparation. A gathering of energy for the billion-year dawn that approaches with the inevitability of orbital mechanics and the gentle persistence of evolutionary time.